Okay, so these PowerPoints are listed on Blackboard and also under organic chemistry. The PDF, the chapter is listed there, so you can either download the PDF and print it. It's 57 pages, or you can just look at it on Blackboard. This kind of summarizes the second half of the book. Well, actually, you don't have the second half of the book. I took it out for the custom edition. We're going to kind of cover a lot of stuff. Organic, biochemistry, synthetic polymers. There's a lot of information here. Help if I went back up and started at the beginning. So, organic chemistry, completely different from what you've been studying now. We have a whole bunch of different types of organic compounds. There are literally millions of them. Organic chemistry is the chemistry of carbon-based compounds. Why are there so many? Because carbon atoms can bond to other carbon atoms and also other elements. So there's such an unlimited numbers of combinations we can make. And there are many different ways to arrange the same atoms in a carbon-based compound. For example, if I started with, let's just look at carbon and hydrogen. I start with 4 carbons. I put in hydrogen. Carbon has 4 bonds. I can have a compound that looks like this. If I gave you all the hydrogens and carbons and asked you to put them together, somebody might put them together like this. Same number of carbons, same number of hydrogens. Arranged slightly different. Different compounds, different properties. So that's just with 4 carbons. When you get 6 carbons, stick an oxygen in there, you can see we can make quite a few different compounds. Hydrocarbons are compounds composed of carbon and hydrogen, which all the carbon-carbon bonds are single bonds. We're not going to get too much into nomenclature because that's a whole different avenue. But basically here we have, you look at the longest chain of carbons, in this case it's 1, 2, 3, 4, 5 across. So that would be pentane, A and E. These are all single bonds. And we see we have CH3 group attached here, here, and here. Those are called methyl groups, and we'll get into that. And it turns out they're in the 2, 2, 4 position. So this is 2, 2, 4 trimethylpentane. You might see a structure written like this. You might see the line structure and a condensed structure. You can also put them in a ring. And those are cyclohydrocarbons. The 2,2,4 trimethylpentane, gasoline engines. When they run, it's a timing between the pistons. When they go off, you get a gasoline air mixture, spark plug ignites it, and it blows the piston back down, and that's what drives your car. If it ignites too soon before the piston gets to the top, the piston pushes the crankshaft in the opposite direction. So that's called a pre-ignition knock. In the old days, to get rid of that, they would put lead in the gasoline. So you had leaded and unleaded. Now they don't put lead in the gasoline. So straight chain hydrocarbons, where all the carbons are in a straight chain, are likely to pre-ignite. So if you have, gasoline is a mixture of different hydrocarbons. If you have a lot of straight chain hydrocarbons in there, you have what's called a low octane rating. Branch chain hydrocarbons are less likely to pre-knock. So they use 2,2,4-trimethylpentane as an additive. So when you go to your gas station, you have 87, what's the other ones, 94, 89, 87, 89, different octane readings. Those octane readings stand for different percentages of 2,2,4-trimethylpentane in the gasoline. Depending on how your engine is designed, you have to use certain octane readings. Most people drive cars that'll use the 87, the cheapest one. Now, if you have a high-performance car like a Porsche, Mercedes, Lamborghini, you have to use the higher octane readings. So, how many people have Lamborghinis in here? Oh, okay.
I have Volvo Turbo. I had to put that in.
Yeah, or a Volvo, some of the higher, certain cars, you need that higher.
Because they were engineered and set up to run off that kind of octane.
Yes.
85 changed ours to American cars to run off 87.
I tried to get great mine and it did not work good one time.
So if your car runs on 87, putting in the higher octane, not really.
It'll treat treat that a little faster. It's a little quicker.
I think it's more of your imagination.
No, we used to do it when we used to do hot rods before. We'd crank the RPMs up on the throttle and then put higher octane in for racing. Really.
Oh, if you're going to change the engine, but I mean standard engine. If you don't adjust it, if you get adjusted, if it's...
But you will get better gas performance if you put a higher octane. It'll change it.
Not by enough to really justify using it. Most of the engines run
87.
just fine on 87. Then there are hydrocarbons that have a double bond, one or more double bonds in it. Remember I said single bonds, the name ended in ANE. Double bonds, the name ends in ENE. Those are called alkenes. Single bonds are called alkanes. Double bonds are called alkenes. And again, here we see the full-blown structure, the line structure, and what's called the space filler model. Then you're going to have hydrocarbons that have a triple bond. They end in YNE. Those are called alkynes. This is ethine. The common name is called acetylene. All right. This is benzene. Benzene is a 6-membered ring, 6-carbon ring. And it looks like alternating double bonds, but it really isn't alternating double bonds. bonds flip over and around and that, and they just keep circulating. So each of these bond lengths are 1.5 bonds long. These are called arenes, or aromatic compounds, where benzene is the basic part of it. The benzene ring. So here we have BHT, which is a preservative. Just a benzene ring with a methyl group, an OH group, and 3 CCH3 groups. Here we have a benzene ring with a CH3 group, 3 nitro rings, trinitrotoluene, TNT, which is an explosive. All right. Let me move. Probably need to move the recording device to the. We're called now functional groups. We can attach other groups to it. Alcohols. An alcohol has an OH attached to the one of the carbons. At least one. So this one, which has 3 OHs and 3 carbons, is called glycerol, or glycerin. If I had 2 carbons with an OH, that's ethanol. That's the alcohol you drink. You can have 3 carbons, and there's an infinite number of them, so I wouldn't know if I count. With an OH in the middle carbon, that's 2-propanol, commonly known as isopropyl alcohol, which is your rubbing alcohol. And over here we have 2 carbons with an OH on each carbon. That's 1,2-ethadiol, or commonly known as ethylene glycol. And ethylene glycol is found in antifreeze.
What?
Antifreeze for your car. Now the thing is, you can drink ethanol. You don't want to drink ethylene glycol. That will kill you. But some people try to commit suicide by drinking antifreeze. So if they get you in time and get you to the hospital, what they do is they hook you up to an IV of ethanol. The ethanol goes through your body and displaces the ethylene glycol. And a lot of times they will put you in a drug-induced coma, because then when the ethanol starts to leave your body, you go through withdrawal symptoms called PTs. And ethylene glycol tends to taste very sweet, which is why you got to keep it away from animals. A teaspoon which can kill a dog. So if you're out working on your car, make sure your animals aren't anywhere near you. And that's the green antifreeze. For those of you with more modern cars that have the red colored antifreeze, it's not ethylene glycol, it's some other compound in there. Carboxylic acids have this C double bond OOH attached to a carbon. R means any group of carbon atoms. So in this case, we have stearic acid. So we have 17 carbon atoms. And then the COOH. This is the functional group. This makes it a carboxylic acid. Okay? Stearic acid is found in a lot of cosmetics. It's found in cold cream. It's a fatty acid. If I showed you some, it's solid, it's kind of waxy. So if you mix it into a cold cream, it gives it that
thick feeling.
thick, creamy, cold, creamy feeling. And you slop it on your face.
Isn't it true that the wax actually makes you, after waxing their hands, one doesn't actually make your hands sweat a little bit to bring some moisture from inside your hand to the outside of the surface of the skin? If you notice, you put a plastic bag on your hand.
Yeah.
Bag, your hand will sweat, right?
Well, it feels like it's sweating, but your hand's always sweaty.
Right. Okay,
Well, when you put a plastic bag on there, the moisture is coming off is contained in the plastic bag, so it condenses back on your hand, so it feels like it's sweating more. Normally, your hand's sweating right now, but the water vapor is going off into the air. Once you put a plastic bag on there, or a rubber glove or something that contains it,
it'll hold the moisture close to your skin.
well, yeah, because it's not going out into the...
Right, okay, so isn't the wax system the same way?
Yes.
Okay. They have it in cold creams and some soaps, and
Wait, you want to dip your hand in wax?
no, it's just weird.
Oh.
It's just as you see it settle, sometimes you'll see the waxy film to it, and some of the soaps and stuff you see.
Yeah.
And so it is wax, really.
It's not really wax.
There's a type of wax in it.
It's-
It feels waxy. It feels chunky. Like,
wax is more like paraffin.
right.
Yeah, it's a hydrocarbon, yes.
Or is it that fat? You were just saying.
Stearic acid is a fatty acid.
I'm done. So good fat. Good fat on the skin.
Chapter 2 in
Yeah.
We have another functional group is an ether. That's where we have two groups with an oxygen in the middle. So that's an ether. So this one has two carbons, it's called ethyl, so this is diethyl ether. This was the first ever anesthetic, diethyl ether, and really up until the Korean War they were using it in surgeries. It's a liquid, high volatility. They would put you in the operating room, they put a mask over you and drip ether on you, and you would pass out. However, ether is also highly flammable, so it wasn't unusual during surgery to set your patient on fire. Because ether fumes. Then again, you can imagine you have to be careful too, because the ether gets in the air, and now you have a surgeon who's starting to pass out because he's breathing the ether.
So it fixes your tonsils because you got third-degree burns on your face, right?
Well, yes and no. It's a real low temperature flame. So, as long as you didn't set like the bedclothes and that on fire, you're okay. Aldehydes. The R group here is a C double bond O with an H. Carboxylic acid was a C double bond OH. Aldehyde is C double bond OH. If this R is an H rather than a carbon, you have the simplest one, which is formaldehyde, which we all know is a tissue preservative.
And used to preserve the red cherries.
Maraschino cherries?
Yeah, it's an ingredient in there.
Okay.
Did you want cherry to preserve?
If you have two R groups, and they could be the same or different, that's what that R prime stands for. It could be a different R group, or it could be the same R group. You have separated by carbon-oxygen double bond, you have a ketone. This is 2-propanone is the technical name for it. We know it as acetone. So that's what nail polish remover has in it, along with some other things. That's what paint remover has in it. This nail polish remover is paint remover.
Aggressive stuff.
Esters are derivatives of carboxylic acid. Instead of RC double bond OOH, we have RC double bond OR prime. So, here we have an ethyl group and a butyl group. This is ethyl butanoate. On the bottom, I'm showing in the middle here. This is salicylic acid. It has a carboxylic acid group at the top. It has an alcohol at the bottom. If I react it with methanol, I make an ester at the top, acetyl salicylic acid, which is acetyl salicylic acid. Take two and call me in the morning. Aspirin. If I react it with acetic acid, I get methyl salicylate, which is, anybody know? First flavor of Lifesaver. Lifesaver's first flavor when it first came out. Wintergreen. That was one of the ones that you had on the smell test.
And we all messed up.
Yeah, you all this. Yeah. Oh. Then we have our amines. Amines are derivatives of ammonia. Ammonia is NH3. So I can replace one of the H's with an R group. I have an amine. I can replace two of the H's with R groups. I have an amine. I can replace all three H's with an R group, and there's our amines. In this case, this is trimethylamine. Remember, this is a primary amine, a secondary amine, and a tertiary amine. Primary means I have one substitute. Secondary, I have two. Tertiary, I have three. So you go from amines to amides. RC double bond O N R. Kind of looks like a carboxylic acid, but we have nitrogen in there. And again, they're showing chemical name ethanamide, common name acetamide. So you're going to have to be able to identify all these compounds. And let's see what we can do here. So, if I have carbon-carbon single bonds, I'm going to call them alkanes.
Okay.
Okay. If I have a carbon-carbon double bond, that's an alkene. Carbon-carbon triple bond, it's an alkyne. Then we're going to look at functional groups. If I have an R, R means it's a group of carbon atoms, and I have an OH on it, that's an alcohol. If I have an R, O, an O, and another R group. Could be the same, it could be different than the other R group. That's an ether. So I have an R, C double bond O, R prime. That's a ketone. R, C double bond O, OH. It's a carboxylic acid. R, C double bond O, O, R prime. That's an ester. R, C double bond OH. That's an aldehyde. What else we got? RN, R prime, R prime prime. That's an amine. R, C double bond O, N, R, R prime is an amide. Okay, I'm missing any. Amine, amide, aldehyde, ester, ketone, alcohol. And if I have a six-membered ring, it's a benzene. So those are the groups you should be able to recognize. So let me. I'm going back. Sweat it. Okay. All right, so there we got our list. I'm going to draw a couple compounds. You tell me what functional groups are in there. What functional groups are in that? What would that be?
Okay.
A what?
Okay.
Nope.
The one to be
The list is right here.
say that.
Huh?
I need to.
No. It's not a six-membered ring.
Okay.
No. Is there a triple bond? I don't see a triple bond.
Double one.
What do we call a double bond?
Okay.
Alkene.
Gee, that was easy.
Even though I drew it in a circle. Okay. What's that?
Alkyne, trouble line,
what? Alpine.
No. What do I have there? In the middle, what is that? A carbon with what? To a what? Okay. This whole mess here is R. This is R prime. Which one is that?
The acid, the carbon.
No. No. Ketone.
Showing up in, I can see him now. Get a hung.
It's an amine.
Huh?
It's an amine, yes.
Amine.
If you see a nitrogen, you only have two choices. It's either an amine or an amide. If you don't see a carbon-oxygen double bond, it's an amine.
Where's the amine up again? My glasses.
Bottom one.
In this case, the R prime and the R prime prime are hydrogens.
So CH3 and CH2 is a R.
That's an R.
And NH2 is what?
Amine. Okay, let me...
Double R bond, two R. Good. Oh, amide.
Ester.
Amide.
How can it be amide? Do you see a nitrogen?
Ester.
Only those two in here. Only
Ester.
Ester.
Let's see here. How's it? It's ester that has
CO.
R. C double bond O. O. R prime. Ester. You got to be able to recognize the functional groups.
Hey, question. In your in that top right column, is that bromine?
No.
Say. It'd be out.
This?
That one. And
Benzene.
benzene. I couldn't read.
Bromine is Br. It's an element.
I couldn't read. I'm sorry.
Can you leave that up for 1 second?
All right. We can do some more. Stop this. Okay, like I said, the only way to do this is to practice. After you look at them for 30 years like I have, it's pretty easy to pick them out. So, as you saw tonight in the practice, I put a bunch of different functional groups in a compound. So we can have difunctional compounds. So here's one. We got on this end a carboxylic acid functional group, and on this end we have an amine. And this is commonly known as GABA, gamma aminobutyric acid. A lot of people buy those as supplements. All right. basically that was it for organic. And really what I'm going to do, let's go back, what I should have done. One thing they didn't give you, but I will give you. When you have groups attached, if you have a CH3 group, or actually prefixes, you can have CH4 is methane. So a CH3 group where we attach this. So we're going to attach this to some R. This is called a methyl. CH3CH3, or 2 carbons, is ethane. So CH3CH2, or we're going to attach it to something else, is called ethyl. CH3CH2, CH3 is propane. CH3, CH2, CH2, where we attach it to something else is a propyl group. All right. CH3, CH2, CH2, CH3 is butane. I'm not going to draw the whole thing over here. We just remove one hydrogen, and that'll be a butyl group. CH3, CH2, 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 CH3, 5 groups is pentane. That'll be pentyl. Okay. 6 carbons would be hexane. 7 carbons would be heptane. 8 carbons would be octane. 9 carbons would be nonane. And 10 carbons, decane. So you know if somebody's talking about a propyl group, they're talking about a group of 3 carbons attached to it. So really, the 2 chains, methyl, ethyl, propyl, and butyl, or methane, ethane, propane, and butane. After that, the prefixes are just 5 pentane, think of pentagon, 6 hexane, 7 heptane, 8 octane, 9 is nonane, and 10 is decane. Yes?
What is the iso and the isopropyl alcohol?
Isopropyl alcohol, since you asked. If I draw 3 carbons, this propyl means propane, 3 carbons. If I put the alcohol here on the N carbon, this is the first carbon, so it's 1 propanol. I can also put it on the second carbon. This is 2 propanol. What is here is called commonly isopropyl alcohol. It means in the second position. When you have 2 compounds that are essentially the same number of atoms, just rearranged. They're called isomers. So iso comes from isomer. So this is the isomer of 1-propanol, which is 2-propanol. Now obviously, as you get more carbons in that, it gets more and more complicated, but that's where it comes from. And it's just a common name when it first started out. And it just kind of stuck. There's a lot of common names for ethanoic acid. We don't call anything ethanoic acid. Common name is acetic acid. We very seldom use 2-propanol. We call it acetone. So there's a lot of common names that started out when they were first making organic compounds that kind of stuck. Which everybody recognizes. Because originally, and didn't talk about this, people thought that there was something magical and mystical about organic compounds. Because early chemists could make all kinds of inorganic compounds, but they couldn't make an organic compound from scratch. So a man named Wöhler used ammonia and I forgot what else, and he synthesized urea. So that was the first indication that, hey, there's nothing really special about organic biomolecules, the molecules of life. It's just, you can make them. So there wasn't anything mystical about them. All right. So we talk about biomolecules. We're really talking about organic chemistry, but on a large scale molecule. If you were to take Chem 132, if you ever find it somewhere, or organic chemistry, and find out how you put organic molecules together, biomolecules are just the same, except we're using large number of carbon atoms. Remember I talked about formic acid? Formic acid was HCOOH, little small molecule. Stearic acid had 17 carbon atoms. Well, still, they're both carboxylic acids. So formic acid, stearic acid is a biomolecule. Large molecules. So here we're talking about, first one we're going to talk about is carbohydrates. We're going to talk about monosaccharides, disaccharides, polysaccharides. Then we're going to talk about amino acids and proteins, triglycerides, and steroids. So different types. So monosaccharide, mono meaning one, saccharide. Saccharide is kind of like sugar. So we have one basic building block. So here we have fructose. If we look at fructose, what do we see? We see an R, C double bond O R. We see a ketone functional group. We also see a bunch of OHs attached to R's, and OHs were alcohols. If we look at glucose, we see a bunch of the alcohols. We don't see a C double bond O. We see an R C double bond O H, which is an aldehyde group. And here we have something that looks like glucose, but you can see here the OH is on the opposite side. It's on the left rather than the right. This is a different monosaccharide called galactose. Now later on, if we have time, I'm going to do what's chapter 18 in your book, which talks about metabolism. We'll go through glycolysis. Glucose and fructose, galactose have these straight chain forms. They also have a ring form. So here's glucose. if I take, right here, okay, this oxygen, bring it up here, the electron pair, attach it here, this comes out, this hydrogen goes here, I get this. The ring form. This is this oxygen. So we say 1, 2, 3, 4, 5, 6. Okay. Now when I attack this C double bond O, I can either attack it from the left or the right. If I go one way, you see in the ring, and that's what it's heavy here because it means the ring's in the plane, I get the OH above the ring. If I come in from the other side, I get the OH below the ring. And the OH is above the ring, this is called beta. And when it's below the ring, it's called alpha. Now you see these, in between these three are double arrows. So it's equilibrium. So it constantly in solution shifts from the straight chain, the open chain, to this ring form, back to the open chain, back to this ring form. Constantly goes back and forth in solution in your body. Same thing happens with galactose. So you see that you can form this 6-membered ring. If you look at fructose, you get this oxygen, comes up here and attacks the ketone. So instead of a 6-membered ring, you get a 5-membered ring with fructose. And again, these are all in equilibrium with each other. Now, maltose is a disaccharide. So we take 2 monosaccharides. In this case, we're taking glucose and glucose, 2 glucose monosaccharides, and linking them together with this oxygen. So now, what functional group is this? No. What's all this mess going to be called? It's ether. This is an R-O-R. This is an ether. Now, in biochemistry, they have another term for it. It's called the glycosidic bond. All that means is that it's a bond that holds together 2 monosaccharides. So this is maltose, which is malt sugar. Now that was the one that you had if you put a piece of potato, raw potato, on your tongue. After a while, it changes the flavor. Well, that's the sugar you form, maltose. What if we take glucose and fructose and join them? Glucose and fructose makes a disaccharide called sucrose. That's your common table sugar. And you can see how in this ether linkage, the glycosidic bond, both linkages are below the ring. This is also called an alpha linkage. Which becomes much more important when we get to polysaccharides. They said alpha is below the ring, beta is above the ring. So this is an alpha linkage. Here we have galactose and glucose comes together. And that makes lactose, milk sugar. Notice again, here we have one below the ring and one above the ring. This is a beta linkage.
Oh, beta was above.
Beta is above, but it's above on this side. It's actually a beta alpha linkage. So a lot of people have trouble with lactose. They can't stand it. They won't tolerate it. The lactose intolerant. The problem with their enzymes breaking that linkage. So if they eat a lot of dairy products and that, you pay for it later. So that's just putting two saccharides. We can put a whole bunch of them together. This is amylose. What this means with this N here means this is a whole bunch of them. This is a polysaccharide. It could be 20, it could be 40, it could be 80. They're all linked with the alpha linkage. So amylopectin or glycogen, see we have a whole bunch linked, all alpha linkages, but now we have a branch coming off. And again, alpha linkage. This is how your body stores glucose. It's glycogen in your muscles, in your liver. Because obviously we need energy to move, to think, to do whatever we're doing, just to live. But we're not constantly eating. I am, but most people aren't constantly eating. So when you're not eating, you gotta, just like a battery, you're discharging your energy. You have to have someplace to store that energy. Otherwise, you have to constantly eat it. So you store it in terms of glycogen. Here's cellulose. Notice the linkage. It's a beta linkage. Again, it's a long chain of glucose. So this is like the paper towel. In our body, we do not have enzymes that can break that linkage. So it just stays as cellulose. It doesn't come apart. Whereas the amylopectin, which we saw earlier, alpha linkages, it's also called starch. We break apart into, eventually we can break apart into glucose, what we need for energy. So we can eat starch, we get energy. We eat cellulose, nothing. It goes right through us. So that's why eat salt, there's no calories in there, because you're not breaking it down. It goes right through it, we call it roughage, and you may not feel drained. So.
But animals have that process, right?
Some animals, cows and that, actually have bacteria in their stomach that can break that, which is why cows eat grass. Not people. So yeah, you can eat all the lettuce and that you want. You'll get some vitamins and that and whatever's in there, but you won't get any energy. There's no calories, very little calories in there. So now potatoes, when the inside of the potato is the starch, you get the energy from that, because starch you can break down. Skin,
You get minerals.
what?
But did you get energy from anything else, like protein?
Proteins, and then you get, yeah, meat in there. And there's certain vegetables. Soy. People eat tofu. What?
We had a bunch of stuff in spinach.
You get a lot of minerals in that, and
Nice.
vitamins, in terms of energy producing.
Carbs, sugar, carbs, proteins.
Well, sugar is a carb.
Some are fast, breakdown, fast energy source.
Well, if you look at it, when you take table sugar, sucrose, you said it was a disaccharide? Okay, you break it down right away. Boom. All right, give a kid a candy bar and you'll see. All right? Quick pick me up sugar. Did you hear about the sugar crash?
Yeah.
Okay. Carbohydrates, your pastas, your starches, long chains. A lot of glucose molecules, but they're all tied together. You got to start breaking them down. Lasts longer. That's why people who run marathons usually carbo load the day before. They eat a lot of pastas and that because that energy will last longer. If you look at those 5-hour energy drinks, they have carbohydrates, long chain carbohydrates. That's what gives you those. If they just put sugar in there, you go for about 30 minutes and then you crash and fall asleep.
How about heavy protein, like meats?
What about it?
Secondary.
Do they break down way slower, right?